Hello, everyone. So I'm Daan Leijen from Microsoft Research, and this is joint work with Sebastian Burckhardt and Jonathan Protzenko at Microsoft Research, and Manuel Fähndrich, who's now at Google. And I'm going to talk about the Global Sequence Protocol, and it's a really exciting work, I think, if you were interested in writing cloud-based applications, because it gives you a much higher level of abstraction for replicated shared state. And it's robust, which means it works well with bad or failing or slow or offline connections. So here's kind of the overview of what kind of applications we want to make. We want to make applications that are basically distributed. It runs on many devices, but you still want to communicate between all of them through the cloud or between different people's accounts. So during my talk, as a running example, I'll do something really simple. I will have a bird sighting application where there's many, usually guys, walk around with their phones in nature, and then they see a bird and they want to count how many of these birds they see. So that will be my running example. But in general, it's of course, you can make it as complex as you want. And it should scale up to really big applications. So at Microsoft Research, our biggest one is the Touch Develop IDE that we're using, which uses this protocol that I'm going to describe in the background. So what kind of abstraction am I thinking of? So normally, I think there's different programming models, how people now write these kind of applications. And one important one is kind of the web apps with shared state. So you basically have a big server somewhere which has persistent cloud storage. And then you can, all the individual devices, they issue queries on these, on the cloud service. And in that way, they communicate information between each other. And usually this is really tricky to get right. Especially if you have to deal with, for example, if you want to make sure that you keep being consistent, often you have to issue your request or your queries and updates as a transaction. But if you're, for example, on a device, you may be offline or the connection doesn't work very well and it may easily fail. And then it's very hard to think about how do you handle these failures. And how do you handle when connections are really bad or when someone enters a plane and cannot be connected at all? And what do you do when they come back out of the plane and connect again? So we wanted to look for something that solves a lot of these issues. And the way we do it is through replicated shared state. And here you have kind of a very generic service with cloud storage. But all the individual apps, they treat it as if they have one huge global memory that they can just access and query, but I'm giving it very special semantics, basically with eventual consistency. I'll get to that. And this kind of model is really preferable because it allows you to kind of abstract away from dealing with all the possible failure situations, for example, or dealing with the granularity of your transactions. So this is basically, as a really simple example. Oh my God, yeah. So as a true functional programmer, I really don't like to show this slide, but I really like true global variables. So not just regular global variables, no, like the worst ones possible. Truly global, which means they're shared between the different applications running on different devices. So it would be really nice if you could somehow say I have a cloud integer called count, and then when I see a bird, I will update that count by 1. And I wrote it a little bit funny here by saying I'm going to read the count, so the read operation, add 1 to it, and then I'm going to write to the count. And later it will become apparent while I write it like this, but I make very explicit, you kind of issue certain operations on this data type. In this case, the cloud integer. So the nice thing about writing it this way, instead of how people do it nowadays, is there's no noise. There's no error handling here. There's no transaction boundary. There's no transaction actually that you can see. There's like nothing going on. But under the global sequence protocol, this is very robust code. It works, you know, when there's bad connections, it actually becomes eventually consistent, It works when you're offline. And this is what I'm going to describe now. So the problem with just coming up with such an abstraction is that you need to think about, well, what does it actually mean? So what is your semantic model? And in this case, we often think about what is the consistency model? And two, can you actually implement it robustly and efficiently? And I'm going to address both of those questions. So first of all, so what does it all mean, and what do we want, what guarantees do we want to give? So normally we think about, in terms of memory models, we think about consistency models. So we have strong consistency models, like linearizability and sequential consistency. And then you have weaker ones, which we call eventual consistency, where you kind of can wait a little bit before everybody agrees on what certain values are. In the paper, I think we describe all of the different variations of that. So the GSP protocol will definitely be in the eventually consistent space. And why? Because if you want to be like strongly consistent, you kind of lock yourself into a synchronized model. But in our case, we really want to be performant and be very asynchronous. So we're going to choose an eventually consistent model, so all operations can execute locally and they can always continue, even if they're bad or slow communication among the channels. So the way we're going to do that, we're going to kind of start with a very common memory model called TSO to develop our model called GSP. So we're kind of going to start with the total store order, and this is a weak memory model, which is very widely used, for example, on x86. And in essence, all your writes are somewhat delayed, so they're asynchronous, but all your reads are synchronous. And among the weak memory models, TSO is, I think, partly popular because it's quite well understood by developers. And part of that is, I think, because there's an operational model for it. And I'm going to show you right now how that works. So the idea is that you have a bunch of CPUs in your computer, and they all have a coherent shared memory underneath it. And what each CPU does is they have a little store buffer, and all the updates all the writes to the memory go through this local store buffer. So they're somewhat delayed, like someone else may not yet see your writes, right? But all your reads, they first look in the store buffer. So you read your own writes synchronously before they look into the main memory. And this is how you can all create really fun race conditions between concurrent programs. But this is at least well understood, and I think partly because it has this operational model that you can think about. Well, some other memory models, they're really only specified through axiomatic semantics, and it's much harder for humans to think about it that way. So the stores are asynchronous, but the reads are still synchronous. So this is how we're going to take the next step to the GSP model, and we're going to apply this memory model, but now to the cloud. So that means we have to think about, what if your communication channel is really slow or unreliable, or you're even offline? So what we're going to do is we're going to make the reads also delayed. So it's going to look a little bit like this. So this is the global sequence protocol. And then instead of a coherent shared memory, we'll have there will be our cloud, and we're going to rely on reliable total order broadcast, RTOB. And this is well studied and well known in the community. And it basically means we have a reliable way of sending messages in a total order, if the messages can get out, of course. So now you have update operations again, and we still have our update buffer. But as you can see, there's also a local replica, and all the reads see immediately their own updates, just like in TSO. But the big difference is that the buffer updates are now both ways, right? So the reads are delayed too. So this also means that in the GSP model, we also assume that everybody has a local replica of the entire state. So for the bird sighting application, everybody will have the count of the current birds on their phone. So this is basically the essence of the model and why we can make sure that everything can go asynchronous. And I will give more examples of how that works out in practice. So we call, the global sequence protocol, it's like the TSO of distributed systems. And yeah, it asynchronously propagates and consistently orders all the updates. And the nice thing is that we can implement it to be persistent and robust under failures, but we can hide all of this complexity. So it really becomes a real abstraction. And moreover, and that's something that's really crucial to all of this, is that we're using an abstract data model. That means we have all the updates are not just stores to some memory location, they're actually operations on the data. This is why in the beginning I said, oh, it's like a write operation, and later we'll see examples of others. So everything is like a data type. So we could have, we call it register, which is basically like a memory location where you just have a read and a write operations. But we could also have counters where you have read and add operations instead of writing, or key value stores or sets, and I'll give many more examples of those. And I'll give you a real good example soon why we need these different kinds of operations. But it's important to think of not of its side effect of what's going to happen, but of like a log of all the operations you're going to perform. So I'm going to give an example of that. First we call it core GSP, and then later I'm going to extend that to transactional global sequence protocol. Yeah, so let me show you a example of a local execution where we have a bunch of writes to 3 memory locations, X, Y, and Z. And we're going to model locally, we always have like the confirmed log of operations, and that's really your local replica of the state, but we're going to abstractly represent it as an entire log of all the operations you've done. And then, of course, you can optimize it by, in the end, of like a certain state that represents that. And then there's the unconfirmed log of operations, and that's basically your store buffer, your update buffer that you're still going to process. And that can also be, of course, represented more efficiently in an implementation, but in the abstract model, again, it's just a log of all the operations that are being performed on a data type. So here's how it's going to work out. Suppose we're at client A, and we have a bunch of confirmed operations, a write to X of 1 done by A write of X of 3 done by B, and a write of A to Y of 2. And then, maybe A is going to write 3 to the location Z, and it's going to send it to its unconfirmed update buffer, and also to the total order broadcast to all the other clients that may be there. And then we get a state that's like X is 3, Y is 2, and Z is 3. Mm-hmm. So now we're going to write a little more. We're going to write X0. So again, it will be sent to the total order broadcast, and it will be in our unconfirmed queue. And then we may gonna receive echoes from the reliable total order broadcast. So for example, we may actually see our own write that had happened. We may see it back. And maybe I'll do that again. So it's coming out. So the third write by A to Z is 3. Is coming back from the reliable total order broadcast. And now we know, oh, it actually happened. And we remove it from our unconfirmed queue to the confirmed one. But there may also be writes that come from other people. So there might be a write that was done by B to Y. And at that point, our Y location gets updated to 4. Or maybe B wrote to X too. So let's see if that comes back. So this is an important case. So B wrote to X the location 4, but we keep X unchanged to 0. So here's why it's important to have a total order broadcast. Because we receive an echo first of the write to X by B, we know it occurred before we are going to do our write. So the reliable total order broadcast also serves as a, how do you call that, a decision maker that in the end orders all writes in a particular order. So the last writer wins in this particular case because it's a register. So that's an important part of all of this. So the nice thing is you can think about it as in a very abstract way in this way, while we can actually provide you with a very reliable implementation of this total order broadcasting. So here's the problem, of course. Maybe people have already seen that. So the current state that when you issue an update operation may be different than the time that it's actually taking effect. And this is basically the idea of race conditions. So, for example, our bird example has a particular race condition because it reads some particular count value and then it's going to write another one. But by the time the write actually takes place, the count may have been updated in the meantime, right? So client A may execute a read on the count and then say it's 0, and then B may do the same. And then they both may issue a write operation where they set the count to 1. And then, oops, we lost one siding, right? They both saw it, but we get 2 individual write operations. So how do you solve this? So this is, well known. People do this on x86 and all kinds of computers. And everybody says, oh, we need to put in a lock and do a particular transaction or do a compare exchange, which is like a lock. But I think there are much better ways to do it if you can deal with eventual consistency. And the way we solve it is by saying, no, you have to be more abstract in your operations. So instead of just issuing reads and writes, we're going to use a higher level operation. We're going to say what our intention is. We're going to say if we do a bird sighting, we're going to add 1. And that will be our write operation. And we're going to instead both execute an add operation. And our log of operation will now be 2 adds, right? And we get indeed the right value. So a way to conflict resolution is by saying, oh, we're going to use higher level operations, and instead of just writes, we're going to have very rich semantics on our abstract data types. And this is a trick that works always. So you make sure that you define the read operation over the log of operations you performed. And the read is the one that actually does conflict resolution instead of locking or some other merge operation. So the nice thing of doing it this way is that we can make a generic server for this GSP protocol, and we show this in the paper, which is, and we show how it can deal with bad connections and exceptions and all these kind of things. And the semantics of your data types can be programmed on the client. So you don't have to make a new server every time you think of a new data type. You can actually do this on the client and come up with your own abstractions. Man, I should talk faster or give shorter talks. I'll talk a little faster. So here's some weaknesses which we want to address. So one of them is we would like to do a whole bunch of updates, often atomically. So we want to say, oh, a customer did some transaction, and now you want to update the amount of product, and you want to add the actual transaction and maybe even the customer. And it all should be done in one go, because otherwise you may violate some invariants that exist. Another thing is that you don't want kind of updates from outside that have been done by other clients to just occur randomly while your code is executing. And also, sometimes you do need a real transaction where you want to make sure that your operation is actually performed. This is like sometimes you do want a true synchronized operation. For example, if you withdraw money from the bank, you want to kind of confirm that it really happened. And we can support all of these 3 things quite nicely. So we're going to bundle all updates together, and such bundles of updates are going to be called transactions. And then we're going to do explicitly push at a certain point all the operations you want to perform. And at a certain point, when you want to see what others have been doing, you do an explicit pool operation. And we can do synchronized behavior to a confirmed property. And all of these three are very easy to support. So all the updates you're doing while your program is executed, they're all bundled in a transaction. And the nice thing is they can never fail. They will all be performed at one go, but they can never fail. Just a bundle of updates, but they can have rich semantics again, right? Like add operations, for example. And then these bundles, instead of just having them sent and received all the time, it only happens when you actually say push or pull. So the nice thing is that we now get away from regular transaction boundaries, which have always have this tension between them, right? You want them to be as big as possible because that's certainly correct, but you also want them to be as small as possible because that allows for more concurrency and efficiency. So how small can you make it before you're incorrect is always the problem. So not in our case, because they cannot fail and they have no other implications, we just make them usually really big. So for example, in Touch Develop, in the UI, there's like an implicit event loop, and around that event loop, we do the push and pull for you. So that means that during an event, just like in JavaScript, for example, there will be no races or interaction, and then all your updates you perform will be done in one transaction bundle through the push and the pull. And through the confirmed attribute, we can make blocking operations that make sure that certain operations are truly performed. So now you can actually wait for things and make sure your bank transaction really goes through. So it's really nice that we can go from a much more weak, eventual consistent system to a more stronger synchronized operations within the same model. I have very little time, but I'll try to show you one more thing. So one thing we did in Touch Develop is build a bunch of richer data types for you that allow you to build your own data types quite easily, like a data model. And we have a bunch of basic ones, like the register and the numbers that you can add and strings and those kind of things. But then the structured ones, those are really powerful. And we kind of needed two kinds. One is a table, which gives you identity. So you can add a new row to a table, and it's ordered table, so it gets to the end of all the other rows. And you can delete rows in there. And it's almost like giving you objects, where a row is like an object, because you can create a new row, it has an identity, and you can later delete it, and you can refer to it. And we also needed something that's called an index. And this is basically an infinite key value store, where everything has an initial value already, and you can immediately start using it. I don't think I have enough time to go through this example. Well, maybe I have like 2 minutes. Yeah, I think we can do it. So first I'll give you a wrong example with a table to give you a good feel for what these two abstractions are. So here I have a cloud table of birds, and they contain basically rows, and the rows contain a name and a count. And then if I see some bird, I find that name, I find the row that corresponds to that bird, and then I add one to its count. Simple enough. But we'll see that the finding kind of goes wrong, and that's why we should have used an index instead, which I'll show later. So here's the find function. So how do you find it? What? I didn't. It should be var bird without find itself. That would not work. Just var bird. Sorry about that. And then for each bird in the bird, so I'm going through all the rows, for each row in the row. If I find a row with the right name, then I'm done. And if not, I create a new row, right? And I'm going to write the name of the bird right there. But of course, this won't work, as you can now already understand, because it will lead to races where two people may create duplicate rows at that point. So you don't want, in this case, I had the wrong abstraction for what you want to do. So tables are very important, but here it's not correct. So here you would like to use one of these index data types. And here you say an index has like a key value, in this case names, and it has counts. And they are implicitly exist for all the possible names already. So a citing would just be indexed by the name and add one to the count. And it would just work, which is great. All right. Very exciting, I think. We're working at this in many other domains. We have a generic server for touch developed that implements all of this. And we're now trying to apply the same work for geo-replications among data servers for Microsoft. And it seems to all work out really well. So that's good. Any questions?
Thank you. Drawing to your distinction between the bird count example and the withdrawal of monies. In the first case, if you use the correct data structure, it's quite all right to just be pushing your updates. But in the second case, you need to wait for a confirmation for the withdrawal. I'm not clear whether your language gives me support to find that there are different cases.
Right. So
whether the types are doing it or nothing, whether I need to know about it, I, the programmer.
Oh, right. So what I sketched here, there might be type systems that will really help out. And there may be great programming language construct that may really help out. But what we did now is basically just have a basic model that lets you do all these things without saying how the language should be designed. So for the bank, yeah, you have to think yourself about what is the semantics I want and how should I achieve that? And there's no type system that warns you of anything. It was the same with the race condition on the bird. Still, as a programmer, that's like an essential thing you have to think about. I don't think we can abstract that away at this point in time. And right, with the bank, the good thing though is that our model supports both. Like we can do synchronized interlocked operations with the cost suddenly of blocking operations and waiting. And we can do eventually consistent operations, which gives you asynchronicity and robustness under bad connections.
So I've got two questions. One is similar to Sophia's. So the bird application, if you do it properly and you use add, then you've got two people, each with the app. One gets on an airplane, but they see a few birds on the airplane, but when they get off the airplane and they get a connection again, that's fine. They just get added in, everything's fine.
Yes.
But now somebody on the airplane does a transaction with their bank.
Right.
What happens? Because you're waiting to sync, but they're on the plane. They can't sync.
Right.
Their phone just goes dead, waiting to hear back from the bank.
Right. No, exactly, right? So this is...
That's good, is it?
Well, yeah, right. That's good. So if you do the withdrawal on the plane, at this time you do a blocking operation, you would probably do it with a timeout. So after 5 seconds, the phone will say, sorry, I can't withdraw, you must have a connection. And that's exactly the cost of these. If you want a real transaction where you actually get the money or really reserve the seat, you must have that connection, right?
Okay.
So right, but it supports both, but that's exactly the cost.
Right. So the second question is, the things that seem to work well here are the operations that are commutative. I was sort of surprised you didn't. This is one of the things you want to teach your users, right? Do commutative things. And this is, of course, very similar to CRDTs. And Mark Shapiro, indeed, was around earlier at the conference. So the question is, how does what you're doing relate to CRDTs?
Right. So
and I'll even put it a bit more strongly. Shouldn't I just ignore what you're doing and use CRDTs?
Yes, use CRDTs. They're good. So we can take your favorite CRDT. We can support it in this framework too. So that's a good thing. So this framework supports any kind of CRDT with the right operations. And the other way around, probably not, though. So a nice thing about this model is that with CRDTs, you have to, for each new data type, you have to prove again that the protocol you're devising is working. So here, because you built your things from basic building blocks, it works by construction. So that's a good thing. With regard to commutative data types, right, add works out really well because it's commutative. But because it's reliable total store broadcast, there is a how do you call that? I forgot the English name. Like, there's a judge that says, well, this one wins. Like, there's a last rider that wins. So you can make much more complicated merge and conflict resolution strategies because you can analyze your entire log. And there is someone who, you know, in the end, there is a flip of the coin who wins, right? So you can make much more intricate strategies for resolving conflicts that are not necessarily based on commutative operations. For example, collaborative editing. Awesome. Come talk to me after the talk. Thanks a lot.